So today we're going to talk about Module 11, which is IP4 addressing. So I'm going to kind of go over this module briefly because I do like to do a lot of things in the classroom itself. So let's just get it going and go through some slides here. So network and host portions of an IP4 address structure. So as we know, an IP4 address is a 32-bit hierarchical address that is made up of a network portion and a host portion. The bits within the network portion of the address must be identical for all devices that reside on the same network. Now, the bits within the host portion of the address must be unique to identify a specific host within a network. If two hosts have the same bit pattern in the specified network portion of that 32-bit stream, then those two hosts will reside in the same network. So when determining the network portion versus the host portion, you must look at the 32-bit stream. A subnet mask is used to determine the network and host portions. So as you see here down below, our given IP4 address, and this is for a device that is unique, as you see in the host portion, has a value that is not 0. So 192.168.10.10. So the first section of that, going back to your classes of addresses and remembering, okay, a class A is the range from 0 to 127. Again, 127 being the loopback addresses or loopback range. Then a class B is 128 to 191, and a class C is 192 to 223. So again, when we look at that very first octet here, we can clearly see that this falls into the range of C. Next, you want to go back and try to remember your default subnet masks for each range of address. And if you forget, refer back to the sheets that I handed out in class. So your default for an A your default for B, and your default for C. So what that all means is when we translate those default subnet masks, anything that is a 255, those of you who did understand the conversion portion of the class, those would be translated to all ones. So anything that represents an all one means it's going to match it bit for bit, meaning 192 is going to remain 192. 168 will remain 168, and 10 will remain 10. So these first three octets are the network portion. The last portion is your hosting field, represented here with your subnet mask as a 0. So zeros will identify the hosting fields per address. And in this case, within the range of .0, which is our last octet for a class C, this again can be anything from 0 to 255. So it's very important, or it is very important for you to understand the differences between what represents the host and what represents the network. And we talked about the ANDing procedure multiple times, but we will actually go through examples of doing that, and that's how we find out which is the network number. So to identify the network and host portions of an IP4 address, you need to use the subnet mask. We take the subnet mask and compare it to the IP4 address bit for bit, left to right. The subnet mask does not actually contain the network or the host portion of an IP4 address. It is just a parameter that we use with the ANDing procedure in order to find out which is the network portion and which is the hosting portion. A default gateway IP4 address is required to reach each remote network, as well as a DNS server for IP4. They are required to translate domain names to IP4 addresses. We'll talk about, the DNS server parameters the further along that we go. Now, a prefix length is a less cumbersome method used to identify a subnet mask address. So your prefix length is the number of bits set to 1 in the subnet mask. So once you take that subnet mask, you convert it, as you see here on the slide, then you count the number of ones. So the first 3 that you see here are your default values, okay, for your classes of addresses. Now, the further down you go, you now are jumping into that last octet. So when you are jumping into that last octet and borrowing bits, this is the process of subnetting. But what you want to take away from this is, if I borrow 1 bit in the next section here, so the 4th line down, I'm going to borrow 1 bit from my octets. When you borrow a bit, it now acts as the subnetwork portion. And all you need to do with that, if I borrow a bit, my prefix changes. It's going to change from the default value of 24 to, in this example, /25, because now if I count the number of ones, I now have 25 ones. And that process is going to go all the way down. And then your new subnet mask that you see here, go back to conversions. If I were to convert this 32-bit address back to the decimal, it would be 255.255.255.128. So when you borrow from your hosting fields, which is what we do in order to create subnetworks, but when we borrow from that hosting field, you need to understand that that subnet mask and that prefix needs to change. Now, it is written in slash notation, therefore, count the number of bits in the subnet mask and prepend it with a slash. So as you see on these slides, all of the number of ones per line are prepended to a prefix length. A network address is also referred to as a prefix or a network prefix. Therefore, the prefix length is the number of 1 bits in the subnet mask. Now, on this next slide is that logical ANDing procedure. So an AND is a gate, a digital gate or a logical gate in digital electronics. You don't really need to know much about it except the fact that I will draw it for you just for reference purposes. This is all you're going to need to know about digital electronics. This is not a digital electronics class, but an AND gate kind of looks like this. And what this says is, in this example, if I have inputs, so these are my inputs, and this would be my output. And the only way that I can get a 1 as a result is if I have a 1 and a 1. So, logical and Boolean is used to determine the network address. A logical AND is the comparison of two bits where only a 1 and a 1 produces a 1. Any other combination results in a 0. So, as an example, if I have a 1 and a 1, my output is going to be a 1. It is that simple. If I have a 1 and a 0, my output is a 0. If I have a 0 and a 0, my output is a 0. So the only time I can get a 1 as my result is a 1 and a 1. Now, just for discussion's sake, if I then were to be attached to what is referred to as a NOT gate, okay, a NOT gate simply says that whatever I go in as, I am not when I come out. So in this example, my AND gate had a 0 and a 0, which resulted in the output of a 0. I have a 0 going into my NOT gate. So if I have a 0 going into my NOT gate, my result here would be a 1. So that is really all you need to know about Boolean operation, okay? The only way I can get a true result is a 1 and a 1, which would be represented as a 1. So, to identify the network address, the host IP4 address is logically ANDed bit by bit with the subnet mask to identify the network address. In digital logic, again, 1 represents a true and 0 represents a false. So when you are using an AND operation, both input values must be true or a 1 in order for the result to be also true or a 1. So looking at this example here. So in ANDing, first thing you do is take the digital representation and convert it into binary for the IP4 host address as well as the subnet mask. Once you do that, treat this like a mathematical, not expression, but example. So once you have those two converted to their binary states, then you do your ANDing procedure. And so as you see here, a 1 and a 1 in this first column is going to be resulting in a 1. When you get to the third bit here, a 0 and a 1 is going to be a 0. A 0 and a 1 and all the way through is going to be a 0 in that first octet. When you get to the second octet, your very first bit is a 1 and a 1, which results in a 1. Your second one is a 0 and 1, resulting in a 0, so forth and so on. And you do this entire procedure all the way to the end. Then, once you are done and you have the binary representation of the IP4 network address, you then translate it back to decimal. So, you start again, step 1, convert IP4 addresses and your subnet mask to binary. Okay, so this is step one. Step two is doing your ANDing process. And again, only a 1 plus a 1 results in a 1. Thirdly, you take your result of your ANDing in binary and convert it back to decimal. So what this whole process tells you is, when we're looking at this, the device in question is .10. My associated subnet mask is the default, in this example, of a class C. I translate it to binary, which is my first step. I do my ANDing, which is my second step. And then I take my ANDing result and I convert it back into decimal. So this tells me that the device that is 192.168.10.10 lives on the 192.168.10.0 network. So look at it like this. Let me draw it out. Let me just change that. Hold on one second. I don't want to confuse you. No, I'm going to leave it like that. Okay, so this entire network is assigned 192.168.10.0. I stop my addressing, I go down and I start addressing my devices. Now, because I am a .0 with the prefix of 24, I have not subnetted at all. So I just simply start addressing my devices. And in this network, I can have a range of .1 to .254. Okay, so this would tell us that that .10 is a device on the all-inclusive 192.168.10.0 network. Excuse me. So there are three different types of IP addresses that you need to be familiar with. The network address is the address that is assigned to you. Your host address is the range of addresses you can use within that network. And then your broadcast address, again, is the address that goes out to everyone in your network. So as I look at this example here, in the little bubble, everyone in this bubble belongs to okay, so that is your given address that is assigned to you. Now, again, in this example, I've not done any subnetting. Now, the reason why I can tell I haven't done any subnetting is because they all have the default prefix of a class C. Oh, I'm sorry, I didn't notice it was down here. Okay, so here is a .1 with a slash of 24, a .10 with a slash of 24, a .55, a .101, and a .12. So the first three on all of these devices is the network number, 192.168.10. Now, when you're talking about your ranges of addressing and things of that nature, we're going to start talking about subnetting. So what you want to understand is when we are talking about a network address, it is defined with all zeros in the hosting field, okay, having to do with each particular class. So in this example, my network address is 192.168.10.0 with a prefix of 24. Your first addressable is going to be one above your network address. Again, I am talking about a class C. I know that I can have between 0 and 255. Okay, I already see on this slide, I can't use .0 because that is my assigned network address. I also can't use .255 because that is my assigned broadcast address. What I can use is the range in the middle. So the range in the middle would start from .1 to .254. These are my usable addresses for my devices. So when you're trying to understand this whole dynamic, understand that what you're really doing is just counting up in binary. So your first address, and I'm not going to translate the 192.168.10. I'm not going to convert that. Understand that you would convert that as well to give it your 32 bits. I'm going to concentrate just on that last octet. So my very first scenario is all zeros. My next one would be the 1 going high. My next one would be my 2 going high. My next one so you will continue along this fashion all the way to 254. And then your very last would be all ones. This is your broadcast, it cannot be used. This is your network, it cannot be used. What can be used is .1 to 254. So a network address is an address that represents a specific network. A device belongs to this network if it meets certain criteria. It has the same subnet mask as the network address, which we saw in the previous slide. It has the same network bits as the network address, as indicated by that subnet mask. So in the previous slide, we saw that everybody did indeed have a prefix of 24. It is located on the same broadcast domain as other hosts with the same network address. The network address has all 0 bits in the host portion as determined by that subnet mask. Host addresses are addresses that can be assigned to a device, such as a host computer, a laptop, a smartphone, a web camera, printer, router, etc. The host portion of the address is the bits indicated by zeros in the subnet mask. Host addresses can have any combination of bits in the host portion except for all zeros, because that would be the network address, or all ones, because that would be a broadcast address. Both of those two carry high significance and cannot be used to address your devices. And remembering that a broadcast address is an address that is used when it is required to reach all devices on that IP4 subnet or network. So a little refresher here, we've talked about these message types before. Unicast transmission is sending a packet to one destination IP address. A source IP address can only be a unicast address because the packet can only originate from one single source. For example, here the PC at 172.16.4.1 sends a unicast packet to the printer at 172.16.4.253. So 1 to 1. A broadcast transmission is sending a packet to all other destination IP addresses. A broadcast packet has a destination IP address with all ones in the host portion or 32 1 bits. A broadcast may be directed or limited. A directed broadcast is sent to all hosts on a specific network. So, as you saw in the previous slide, if I were going to send a broadcast to that one particular network of 192.168.10.0, it would go out as a 192.168.10.255. If I'm going to send it out to my entire network, it would be 255.255.255.255, which would go out to everyone. By default, your routers will not pass a broadcast. They will receive one, and it does not mean that they don't use them. They certainly do for certain things that we'll talk about going further along, but they will not receive a broadcast and then pass it along to another router. For example, PC or the PC at 172.16.4.1 sends a broadcast to all IP addresses. So every single one on that network or on its network of 4.1 would receive, not 4.1, I'm sorry, 4.0, would receive that broadcast. So every single device here, okay? They all are part of the 4 network, so understand that. They're all 4. So the broadcast here would be this would be the network. So the broadcast would be, first usable would be, and the broadcast would be, and the last usable would be, okay? So they're all /24. So network, broadcast, 1 to 24, range of addresses. But when I'm going to send a broadcast, it goes to everyone. In the network. Oops, I'm sorry. This guy's the source. Now, multicast, as we remember, is sending a packet to a multicast address group that we define. A multicast packet is a packet with a destination IP address that is a multicast address. So you are talking about the range of addresses from 224 to 239. So for example, the PC at 172.16.4.1 can send a multicast packet to the multicast group address of 224.10.10.5. So a group is created, okay, and you see on the slide over here, a group is created, and it is the multicast group of 224.10.10.5. So again, 4.1 is the source, but only those that are in the multicast group will receive it. So in this example, these two are defined as being in the multicast group. And so those are the only two that would receive that message. Hosts that receive particular multicast packets are referred to as multicast clients. The multicast clients use services requested by a client program to subscribe to the multicast group. Now, as defined in RFC 1918, public IP addresses are globally routed between internet service providers. Private addresses are common blocks of addresses used by most organizations to assign IP4 addresses to internal hosts. So anyone can use this addressing scheme that is defined under RFC 1918. Private IP4 addresses are not unique and can be used internally within any network. However, they are not globally routable. Doesn't mean they're not routable. They're certainly routable within the organization structure. They do not go out onto the internet, meaning most times your internet service provider would be blocking those addresses, and your internet service providers would also be assigning those addresses. When you take a look at your home network, it is usually going to be a 192 type of address, which is a private addressing scheme. Now, I've talked about this briefly before, and I do want to point it out again. These ranges, these prefixes identify the number of bits that identify the network as we just discussed. So please pay attention. Excuse me, Pay attention. I'm going to write on the board the default values for the classes of addresses. This is what we call traditional addressing or classful. So what I want you to pay attention to, first one, 10.0.0.0/8, no change in that prefix. So that entire network of 10.0.0.0 is for private addressing. Next, when you come down, the 172.16.0.0/12, only a portion of that is private. The rest would be public. So you would have to define the bit value. As you see here, it goes from 0.0 to, 16.0.0 to .31.255.255. And lastly, the 192.168.0.0/16 again means only some of it is private and some of it is public. Now, that being said, I've seen some questions that says, you may get one or two along your path somewhere that will ask you which addresses are public and which ones are private. That's what they're talking about, because that prefix changes between the default of public and the default of private. So pay attention to this parameter here. This slide is not wrong. Okay, this is defined as public addressing, as private addressing, but because our traditional is /8/16 and /24, within the 172 and the 192, some of those are private and some of those are public. Now, we talked a little bit as well about network address translation. So network address translation, NATing, translates private IP4 addresses to public IP4 addresses. It is typically enabled on the edge router, or typically called a border router, the one that is connecting to the internet. So it is the one that lives between your internal network and the internet itself, or your ISP, which represents obviously your internet connection. It translates the internal private address to a public global IP address. The IP4 addresses in the organization's intranet will be translated to public IP4 addresses before being routed to the internet. So in all three of these scenarios, okay, they're identifying the border router for you. So in this case, this is my border router here, or my edge. One and the same. And same thing here, and same thing here. So this is where you would configure NATing, on the edge. Okay, so internally you can see you are using your private addressing schemes. It would get here. This router would say, oh, no, no, no. This router would refer to a NAT pool that we as the administrators create. So what we do is we say, out of our public assignment, out of however many public addresses we have, you decide how much you want to give up for NATing procedures. You create that pool. Now, every time a private address needs to go out onto the intranet, it will grab a public IP address from that pool. Once that conversation is done, that address goes right back into the pool. So you define how many addresses you want to give up. So private addresses are commonly used for educational purposes instead of using a public IP4 address that most likely belongs to another organization. Now you also have special use addresses. You have a loopback address, which begins with 127.0.0.0. And again, don't be so concerned with the ranges of addresses in parentheses. I have never seen a question that asks you the particular ranges. What I have seen is what type of address is a 127. So it doesn't matter if it's a 127.0.0.1, which is what we teach you with. We teach you the very first one. Do understand the range of addresses would be that is inside the parentheses. So when you're trying to identify a loopback address, it doesn't matter what the last three octets are. If it's a 127 in the first octet, you define it as a loopback. Now, I know you've seen this in your labs, a linked local address. A lot of you, when you're doing your labs and you don't get your static configurations correct, and you do an IP config in your command prompt, you will see a 169 address. It is 169.254.0.0 with a slash of 16. Again, there is your range. These are commonly known as the automatic private IP addressing. So sometimes when you do that show IP INT brief, how it is learned would be this APIPA. It is self-assigned by Windows itself. So Windows assumes perhaps you might want to have conversation within your organization. So for local common traffic or conversation within your LAN, they will automatically assign a 169 address. Again, not routable out on the internet, only for internal. Now, this is types of IP4 addressing, legacy classful addressing. So within our legacy classful addressing, which I've talked briefly about before, it is defined in RFC 790. And this is how IP4 addresses were allocated in the early days. So again, your class A is from .0 or 0 to 127 with a prefix of 8. It is an extremely large network with more than 16 million host addresses. And so therefore, it is meant for your large operating ISPs and things of that nature. Your class B is 128 to 191 with a prefix of 16. This is for moderate to large size networks up to approximately 65,000. So maybe your Walmarts, your BJ's, something like that. And then your class C, which is 192 to 224. I'm sorry, there's a typo there. That should be 224. Oh, I'm sorry. No, I'm lying. It is 192 to 223 with a prefix of 24. My apologies. It is for small networks with a maximum of 254 hosts. So what I always refer to as mom and pops, family home-owned businesses that perhaps run out of their home or out of their garage or out of a very small location. Your class D is 224 to 239. This is your multicast block. And then your class E, which is 240 to 255, which is for experimental. Biggest thing with classful addressing is you waste IP4 addresses, and I will explain that much more in detail when we talk about subnetting. So if you look to this pie example on the right-hand side, they pretty much took off one whole half of that pie and gave it to all the big players. And then they sliced it in half again, gave one half to class B, and then they took that again and sliced it in half and gave half of that to C and half of that to D and E. Functional back then, but certainly not in today's networks. So assignment of addresses. The Internet Assigned Numbers Authority, IANA, manages and allocates blocks of IP4 and IP6 addresses to 5 regional internet registries, or RIRs. They are responsible for allocating IP addresses to ISPs who provide the IP4 address blocks to smaller ISPs and organizations. So they are global. So be familiar with their globalness, where they're located. AFRINIC is the African Network Information Center in Africa region. APNIC is the Asia Pacific Network Information Center in the Asia and Pacific region. ARIN is the American Registry for Internet Numbers, which is the North America region. LACNIC is the Regional Latin American and Caribbean IP addressing, and that is for the Latin America and some Caribbean islands. And then lastly, you have RIPE NCC, which is Resolo IP Europeans Network Coordination Center, and that is for Europe, the Middle East, and Central Asia. Now, broadcast domains and segmentation. Many protocols use broadcast or multicast. As an example, we just learned about Address Resolution Protocol, which does use broadcasting to locate other devices. Hosts also send DHCP Discover broadcast to locate a DHCP server. Switches will propagate broadcasts out all interfaces except the interface on which it was received. So in a local area network scenario, broadcasting can be very detrimental. If I were to take this situation here and you see all those switches and just kept adding to all those switches, and if all those switches were 48-port switches, how many broadcasts is being sent out or are being sent out in that scenario? So you could get what is referred to as a broadcast storm that could potentially take down part of your network. So the only device that will stop a broadcast is a router. Routers do not propagate broadcasts. Each router interface that is connected to a broadcast domain or is connected to a broadcast domain, and broadcasts are only propagated within that specific broadcast domain. So switches do not propagate broadcasts. Routers do propagate broadcasts. So know which devices will determine your broadcast domains. It is your routers. So problems with large broadcast domains. Hosts can generate excessive broadcasts and negatively affect the network. Don't forget what a broadcast message is. It goes out to everyone, but there is only one sole device that will answer that request or none at all. So it is a waste of your resources on your devices. The solution is to reduce the size of the network to create smaller broadcast domains in a process called subnetting. The terms subnet and network are often used interchangeably. So, dividing your network address into 117.16.0.0 with the prefix of 16, and taking that and dividing it into 2 subnets of 200 users each, you could subdivide and get a 172.16.0.0 with the prefix of 24 and 172.16.1.0 also with the prefix of 24. So now you have 2 different broadcast domains, each having 200 users, but that router is not going to pass a broadcast from LAN 1 into LAN 2, nor will it take a broadcast from LAN 2 and propagate it into LAN 1. This is why we subnet, one of the reasons why we subnet. And we will talk about that going further along. Now, reasons for segmenting your networks. Subnetting reduces overall network traffic and improves network performance. It can be used to implement security policies between subnets. It can reduce the number of devices affected by abnormal broadcast traffic. And subnets are used for a variety of reasons, which include some of the following here. I can subnet per location. So in this first example, I am subnetting according to floor. So each floor of this building is its own subnetwork. I could subnet according to group or function. So here I have 4 different subnets, one for the administration, one for human resources, one for students, and one for accounting. And I could also subnet according to device type. So I can have all my LANs in one, all the servers in another, and all the printers in another. So how you subnet and reasons for subnetting are a very personal choice within the organization itself. Now, networks are most easily subnetted at that octet boundary of 8, 16, and 24. Those are your classful boundaries. Notice that using a longer prefix length decreases the number of hosts per subnet, which makes sense. If I'm taking away from this hosting field here, okay? Here I get the whole entire enchilada. I get 2 to the 24. 8, 16, 24. Here I'm only getting 2. 8, 16. Here I'm only getting 1. So the longer your prefix, the least amount of hosts per subnet. So again, here I am 2 to the 16, 2 to the 24 in my hosting field. 8 plus 8 plus 8, which gives me this number. Secondly, I am 2 to the 16, 8 plus 8, which is giving me this number. And then lastly, which is the one we will start subnetting with? We always start subnetting with a class C because we're only dealing with 1 octet. If you understand that, I will go ahead and introduce a class B. I will not bother introducing a class A because we have the dynamic of private addressing. So here I have 2 to the 8, which gives me this number here, 254. Now, subnet private versus public address space. Again, enterprise networks will have an intranet. Don't forget about your 3 different scenarios. You have the internet, which is the all-encompassing World Wide Web. You have the intranet, which is your company's internal network, typically utilizing private addressing. And then you have your extranet, which is allowing an external company to come into your intranet. Your DMZ zone, demilitarizing zone, is a company's internet-facing servers. Now understand, this is a part of the company's network which contains resources available to the internet, such as a web server. You're not going to create a web page if no one is going to be allowed to get to that web page. So we create this little scenario, which is referred to as a DMZ zone or demilitarized zone, and that is where we will place our servers, which are hosting public IP addresses so that outside individuals can get to them. Devices, again, in the DMZ are going to utilize your public IP4 addresses. However, internally, a company could use the 10.0.0.0/8/16 or /24 for their network boundary. Your DMZ devices would have to be configured with public IP addresses. But understand, what do you see in this picture? I see my firewall, which is going to protect me. So you will learn about how you go in there and create scenarios on your routers on an actual firewall appliance where you would open up certain things. We talked about a little bit about ports. You would open certain ports on your firewall so that traffic could get to your web browsers. Okay, but your firewall is protecting your internal network, be it your DMZ or be it your internal private network, from the internet. Now, variable length subnet masking. I'm going to just briefly introduce this here. I kind of step away from subnetting because I like to do it again in class on the board. But the left side here, what you're going to take away from VLSM, which stands for Variable Length Subnet Mask. And I'll write that on the board in a moment. So your left side displays the traditional subnetting scheme, where when we start talking about subnetting, we'll learn about different parameters, that which in traditional, everybody has the same amount of hosting fields as you see here. With variable length subnet masking, it means subnet masks will change according to organizational needs. And I can do my first traditional subnetting of all 30s and then take one of those 30s and subnet it again. This is referred to as supernetting. So now you can drill really down deep into what you actually need. So when using variable length subnet mask, always begin by satisfying the host requirements of the largest subnet and then continue subnetting until the host requirements of the smallest subnet are satisfied. And I will do examples in class. But what I want you to take away from this, within tradition, I'm going to write some rules down. Sorry about that. I'm going to do it in class because I can't go back in this presentation when I'm recording. But there are certain things within traditional. Everybody has to have the same subnet mask. All the hosting fields are the same. Things like that, where those will be the things that will change in variable length subnet masking. Take the word for what it is. It's variable. So the word variable is attached to subnet masking, which means your subnet within your organization will be variable according to the needs of how you subnet. Now, IP networking planning is crucial. It's not something that you take lightly. You need to develop a scalable solution to an enterprise network. To develop an IP4 network-wide addressing scheme, you need to know how many subnets are needed, how many hosts a particular subnet will require, what devices are part of the subnet, which parts of your network use private addresses, and which will use public, and many other determining factors. You need to examine the needs of an organization's network usage and how the subnets will be structured. So you're going to perform a network requirement study by looking at the entire network to determine how each area will be segmented. You're then going to determine how many subnets are needed and how many hosts per subnet. You're going to determine DHCP address pools and layer 2 VLAN pools. You're not going to talk about VLANs during this course. That is Cisco 2. The larger IP6 address allows for much easier address planning and allocation than IP4. So conserving IPv6 addresses is not an issue. So this is one of the driving forces for everyone transitioning to IPv6. Within your network, there are 3 different types of devices that require your addresses. You have your end user clients. Most will use DHCP, which is also set up by the administrator, which you'll get to in Cisco 2 or possibly Cisco 3. DHCP is to reduce errors and burden on the network staff itself. IP6 clients can obtain address information using DHCP v6 or SLAC, which we'll talk about within the parameters of Module 12. Your servers and peripheral, you want to give these a predictable static IP address. If someone is trying to print to a printer, you can't have that printer's IP address changing. It needs to remain static. Likewise with other important devices that you deem in your organization. Servers that are accessible from the internet. So servers must have a public IP4 address, which is most often accessed using network address translation. Your intermediary devices. These are devices which are assigned addresses for network management, monitoring, and security. Your gateway. Your routers and firewall devices are gateways for your hosts in that network. That address cannot be changing. So when you are developing an IP addressing scheme, it is generally recommended that you have a set pattern of how addresses are allocated to each type of device. So that is a little bit about your networking and hosting fields, your subnetting, your private versus public, and we will talk more in depthly in class about these parameters.